Okay, welcome everyone once again. So let's do chapter 9. In this video, I will be covering the notes for chapter 9, and then in the next one, we will look at some of the questions from the end of the slides. So, chapter 9, what we're going to do is we will look at hypothesis testing. Okay, so that is the agenda, hypothesis testing. And what we will do in chapter 9 is we will go over these sections, section 1, 2, 3, and 4. Um, so we're not doing the entire chapter 9, and so please make sure that you know what sections we are doing. Okay, just to kind of motivate the topic and introduce you to hypothesis testing, let us think about a context. So let us say we have a city A. Wait, let me just get my pen going. Okay, so let us say we have city A and a city B. Okay, and what we're trying to see is, are the average wealth levels or income levels in the two cities the same or different? In other words, which of the two cities is has a higher income level? So this is often a kind of a point of discussion. So, for example, people saying, "Oh, maybe the income levels are higher in Calgary, or maybe the income levels are higher in Edmonton." So that kind of a comparison. Okay, so we're trying to see which of the two cities do they have do they have the same average income level, or does one city have more than the other? Now, of course, if we were to do a census in both the cities, then we will just find out the income of the entire population, then work out the average and see who's doing better. But in most cases, we don't do a census, we just do a sample, right? So what we are trying to see is, let's say the average income in city A is mu A, and the average income in city B is mu B. So we are saying, are they same or are they not same, right? So this is called hypothesis testing. And what we do is we basically collect a sample, right? And basis of the sample, we will calculate the averages, the sample averages. So we will calculate sample average for city A and sample average for city B. And then we'll calculate some kind of a test statistic. So test statistic would be either the z-score or the t, depending on whether sigma is known or sigma is unknown. Okay, and then we'll compare them to those values in the probability table, and then we'll decide whether the two are same or they are different, right? So this is called hypothesis testing, and typically when we have an equal to sign, this is called a null hypothesis, and then the other one is called alternate hypothesis, and one of them is going to be true. So what we generally say is, can we reject the null? In case we reject the null, then we say, okay, it looks like that the income levels in the two cities are not same. And if we cannot reject the null, then we say, well, looks like that the income levels in the two cities are similar. Okay, and this is kind of the background of hypothesis testing. Now, we will go over different ways of doing hypothesis testing, but you will find in my notes that I've given you some shortcuts on how to do them. And you could either do those shortcuts, or you can just follow the detailed methods as they are laid out in the slides. So just to give you a quick understanding of how you can take, if you want a shortcut, then you ask yourself, okay, is sigma known? Sigma is the population standard deviation. If sigma is known, then obviously you will use z, okay? And so if it is known, right? And if it is unknown, then we will use t distribution with n minus 1 degrees of freedom. Okay, now what we will see is that there are two kinds of tests. Of course, there are two hypotheses, null and alternate, but even there are two kinds of tests. One is called a one-tailed test, and we will see shortly what is a one-tailed test. But the null hypothesis typically takes the form of mu more than equal to or less than equal to, and the other is called a two-tailed test, okay, in which the null typically takes the form of mu equal to, okay. So if it's a one-tailed test, we reject null if p-value, which is going to be 1 times the probability that we will calculate, is less than equal to alpha, okay, or your absolute value of z calculated is more than equal to absolute value of z alpha from table. Okay, now we know absolute values. For example, if I say what is the absolute value of 2, it is 2, but what's the absolute value of minus 2, it is also going to be 2. So you basically take away the negative sign. Okay, now if you're using t, it's the same, it's similar. So you reject null if p-value, which is again going to be 1 times the probability, is less than equal to alpha, or the other rule is absolute value of t calculated is more than equal to absolute value of t alpha from table. Okay, so this calculated value is called the test statistic, and the value from the table is called critical value. And this remains the same whether we use the z table or the t table. Okay, so that was one tail test. Now in the two tail test, what happens is there's a slight change. So we reject null if p-value, which is now going to be twice the probability that we will calculate, is less than equal to alpha, or the other rule is absolute value of z calculated is more than equal to absolute value of z alpha by 2. Okay, so oops, sorry, let's go back. So the absolute value of z alpha by 2. Okay, let me just make it like this. Yeah, so absolute value of z alpha by 2. Similarly, when we are using the t table, we reject null if p-value, which is again twice the probability, is less than equal to alpha, or absolute value of t calculated is more than equal to absolute value of t alpha by 2. Okay, so as you can see, what's happening is that if it's a one-tailed test, p-value, the rule is p-value less than equal to alpha, or the absolute value of z calculated more than equal to absolute value of z alpha from table. And if it's a two-tailed test, then we multiply the probability with 2 to get the p-value. Or for the critical value approach, we say absolute value of z calculated is more than equal to absolute value of z alpha by 2. And when we are using the t table, then we just replace z by t with n minus 1 degrees of freedom. Okay, and we'll see how that works when we go through some of the problems. Okay, so let's go through the notes here. So as I said, we will have a null hypothesis denoted by h naught, which is a statement about a population parameter, and it always has an equal to sign. So let's say the null could be mu1 equal to mu2. It could be mu1 less than equal to mu2, or it could be mu1 more than equal to mu2. Okay, but you will see that there's always an equal to sign in the null hypothesis, and the alternate hypothesis denoted by HA is the opposite of null hypothesis. Okay, and it doesn't have an equal to sign, so the opposite of null is alternate. So when we have an equal to sign, then the alternate would be mu1 not equal to mu2. In this case, it would be mu1 more than mu2, and in this case, it would be mu1 less than mu2. Okay, so this is called a two-tailed test, where we have an equal to sign in the null hypothesis, and this are both called one-tailed tests because we have a greater than or a less than equal to sign. Now, what happens is that sometimes it's easy to formulate the null hypothesis first, and then we can make we can come up with the alternate hypothesis, and in some other cases it's easier to first formulate the alternate and then we formulate the null. So we'll see, depending on the context, which one is easier to identify, right? Sometimes it's easier to identify not H naught, and sometimes HA is easier. And of course, only one of the two is going to be true. Either H naught is going to be true or HA is going to be true. So let's go through some examples on how to formulate the null and the alternate hypothesis. Excuse me. So there is a new teaching method that is better than the old method. So focus on the word better. It is giving us a direction. Okay, a new teaching method better than the old method. A new teaching method that is better than the old method. So that means better is giving us a direction. So new teaching method is better than the old method. So we can first formulate the alternate, and then the opposite is the null hypothesis. And this is a one-tailed test because we have this kind of a sign in the hypothesis. Okay, example 2. A new Salesforce plan or bonus plan increases sales. Okay, so a new plan increases sales. Okay, so wait. So let's say sales new, sales old, alternate sales new, sales old, right? A new Salesforce bonus plan increases sales. Focus on the word increases. There's a direction, and then the opposite is the alternate, the null hypothesis, right? So this is again a one-tailed test. So in both cases, it was easier to first formulate the alternate and then formulate the null. Okay. A new drug is developed with the goal of lowering blood pressure than the existing drug. So let's say drug new, drug old, drug new, drug old. So the new drug lowers blood pressure. So the new drug lowers blood pressure more than the old drug, and then the opposite is the null, right? So again, this is a one-tailed test, right? The new drug lowers than the old one. Okay. The label on a soft drink bottle states that it contains minimum of 67.6. So focus on the word minimum. Again, it gives us some kind of a direction. Minimum of 67.6. Okay. So that means it can contain minimum of 67. So it can be 67.6 or more than 67.6, right? So 67.6 or more than 67.6. So in this case, it was easier for us to formulate the null hypothesis first, and then the opposite is the alternate hypothesis, right? So minimum means it should be a minimum of 67.6 that is equal or more. So again, this is a one-tailed test. So as I said, the equality part always appears in the null hypothesis, right? So this is a one-tailed test, and this is also a one-tailed test, and this is a two-tailed test because we have equal to and not equal to sign here, right? So this is called a lower tail test because in the alternate mu is less than equal to mu naught, the hypothesized value or the hypothesized parameter, and this is upper tail because mu is more than mu naught. Now um, you can either do it this way or the notes that I showed you at the beginning, where we came up with those with the table on how to do hypothesis testing. Remember these notes. Let me just go up and show you. Uh, so let me just, yeah. So in those notes, well, I think I'm not able to pull them up, but anyways, when you do it that and based on those notes, then you just need to remember whether it's a one-tail test or a two-tail test, and then everything else falls into place. And I'll show you how to do that. Okay, so let's jump into a problem. Um, Metro EMS. A city operates, so let's say there's a small town, it operates 20 emergency medical service units. Goal is to respond within 12 minutes. Test whether the targeted response time is being achieved. So let's first make the null and the alternate hypothesis. Okay, so a city operates 20 emergency medical service units. So they have 20 emergency vehicles, and the goal is to respond within 12 minutes. So it can be 12 minutes. So within 12 minutes means 12 minutes or less, right? So 12 minutes or less, and then the opposite is more than 12 minutes. So this again becomes a one-tailed test, right? Because the goal is to respond within 12 minutes. So, oops, yeah, so this is what I was showing you. This is if you follow this way of doing questions, as I explained to you in the beginning, then we just need to know whether it's a one-tailed test or a two-tailed test, and I'll show you that when we get to the questions. So, okay, it's right here. Yeah, so this is the null hypothesis. Mu is less than or equal to 12, and alternate is mu is more than 12, where mu is the mean response time. Now, if we cannot reject the null, that means the EMS is achieving its targeted response time. And if we reject the null, that means the emergency service is not meeting the response goal, and some kind of a follow-up mechanism or follow-up action is required. Okay, so then once we have formulated the null and the alternate, we have to then carry out the hypothesis testing. And what we do is we first ask ourselves, is it a one-tailed test or a two-tailed test, right? Is sigma, the population standard deviation, known or unknown? And then are we going to use the p-value approach or the critical value approach? Now there's also a third approach called the confidence interval approach, which I will explain to you, and this is based on chapter 8. Okay, but we will be using p-value approach and critical value approach. Confidence interval approach I'll just explain to you. Okay, what are the steps? The steps are, we first formulate the null and the alternate hypothesis. Then step 2 is we specify the level of significance alpha, which is usually, so remember in business we have usually we use three confidence levels, 90%, 95%, and 99%, as we saw in chapter 8. So alpha levels are, when it's 90%, then alpha level is 10%. For 95%, alpha level is 5%, and for 99% confidence level, alpha level is 1%. Okay, so these are the three common alpha levels that we'll be using. Of course, collect sample data and compute the test statistic, which I told you is the Z or the T score. Now we use the test statistic, which is either the Z or the T, and we use that to compute the p-value and then reject null if p-value is less than equal to alpha, as we saw in the beginning. Okay, and we will calculate the z-score using the same formula that we learned in chapter 8. Okay, and then we will see how much is the p-value and how much is the alpha. Okay, using the standard normal distribution, and we'll reject the hypothesis if p-value is less than equal to alpha. Okay, so don't worry if these two diagrams are not super clear. I will explain them once again when we do the questions. So let's go back to our emergency vehicles problem. I'm going to give myself a little more space here so that I can do the question. Okay, so remember we already formulated the null and the alternate. So our null was mu less than equal to 12 and alternate was mu more than 12, and it's a one-tailed test. Okay, the average response time for a random sample of 40 medical emergency vehicles is 13.25. So n is 40 and x bar is 13.25. The population standard deviation is 3.2 minutes. Because sigma is given, we will use the z approach or the z distribution. Perform a hypothesis test with a 0.05 level of significance. So when we say 0.05 level of significance, that means this is the value of alpha that is already given to us, and that means we are operating at 95% confidence level. Okay, so we have done this several times now. Excuse me. We'll draw this later. Let's first calculate our test statistic. So z is equal to x bar minus mu over sigma divided by square root of n. So that is 13.25 minus 12. Remember mu is 12, right? Divided by sigma is 3.2 and n is 40. So square root of 40, and this comes to 2.47. Okay, so this comes to 2.47. All right, so now if you draw the z curve, this is 0, this is 2.47, and if you look up the z table, okay, what you will find is that this area is 0.9932. Okay, if the z-score is 2.47, so this area is going to be 1 minus 0.9932. 1 minus 0.9932 is equal to 0.0068. Okay, so now remember we reject null if p-value, and this is a one-tailed test, so p-value is 1 times the probability is less than equal to alpha. So probability is this 0.0068, so that is the p-value. So that is 0.0068. And how much is the alpha in this question? The alpha is 0.05. 0.05. So yes, the p-value is less than or equal to 0.05. So we can reject the null. We can reject null hypothesis, right? Yeah. So this is what we have just done. We formulated the hypothesis, the null, and the alternate, and then alpha level is 0.05. We calculated the z-score to be 2.47, and then we computed the p-value, which was 0.0068, and because p-value is less than equal to alpha, we reject the null. And what does that mean? What it means is that the emergency vehicles is not meeting the response goal of 12 minutes, because you remember the null was mu is less than equal to 12, and alternate is mu is more than 12. So if we reject the null, then that means that it looks like from our data that the emergency vehicles are taking more than 12 minutes. Now, we never say that this is alternate. We don't say that we accept alternate hypothesis. All we say is whether we reject or do not reject the null. So in this case, we do reject the null, and we can say, yes, the emergency vehicles do not meet the response time, and so we need to take up some follow-up action. Right? So as you saw, our alpha is 0.05, right, on the right hand side. And our p-value is 0.0068, so our p-value is less than equal to alpha, so we can reject the null. Okay, now since till now we were using the p-value approach, so let's now use the critical value approach. Okay, so the first three steps are the same. Develop null and alternate. We've already developed. The null was mu less than equal to 12. Alternate was mu more than 12. Level of significance alpha is 0.05. Remember, it's a one-tailed test. Collect sample data. Let's say we already collected the sample data and computed a test statistic. So our test statistic, or z calculated, was 2.47. Okay, now so in the critical value approach, we will use alpha to determine critical value. Now alpha is 0.05, right? So alpha is 0.05. So if this is 0.05 and this is 0.95, okay, and if you look up the z table, then the z should be equal to 1.645. Okay, so compare the test statistic with critical value. Remember the first table that I showed you, we reject null if absolute value of z calculated is more than equal to absolute value of z alpha from table. So absolute value of z calculated, so absolute value of 2.47 versus absolute value of 1.645. So this is 2.47, and this is more than equal to 1.645, which means we can reject the null. So as you can see, it doesn't matter whether we use the critical value approach or the p-value approach, we should still get the same answer, and in both cases we reject the null. Okay, now if you don't want to use this absolute value approach, what you can do is, we already know that it's a one-tailed test, and we know sigma, population standard deviation, so we are going to use the z-table approach. Okay, and we use the z-table to find the critical value, z alpha, such that with an area of alpha in the lower or upper tail. Now, we need to find out whether it's a lower tail test or an upper tail test, right? So remember that in this case, it's an upper tail test because our null is mu is less than equal to 12 and alternate is mu is more than 12. So this is not only a one-tail test, but this also is an upper tail test. So we reject null if z is more than equal to z alpha. So our z calculated is 2.47 and z alpha from the table was 1.645. So this is more than the value from the table or the critical value. So this is called the critical value, just as before. And this is called the test statistic. And so because test statistic is more than the critical value, we can reject the null. So either way is fine. Either you do this or you can use the absolute values. So what happens with the absolute values is then you don't need to figure out whether you're in the lower tail or the upper tail. Okay, so z absolute value of z calculated versus absolute value of z alpha. And if this is more than that, then we reject the null. So in this case, we don't need to worry whether it's a lower tail test or upper tail test. Okay, but both are the same, they give you the same result. right? So this is just an example. If you are on the lower side, you reject null in case z alpha is less than, yeah, so do not so this is called the rejection region. The red is called the rejection region, and blue is the area where you don't reject the null. So you only reject the null if your calculated value is more extreme, right, than the value that you get from the table, right? So this is on the upper tail side. You And again, the red region is the rejection region, and sorry, and the blue is the non-rejection region. So going back to the same example, and these are the steps we've already discussed, and I've already shown you. So we calculated null, formulated the null and the alternate, and then the alpha level is 0.05, z calculated is 2.47, and then for alpha 0.05, the z alpha from table, or the critical value from the table, is 1.645. We reject null if z is more than equal to the value from the table, which is the case, and so we can reject the null. Now note the result remains the same whether we use the p-value approach or the critical value approach. The change of the approach doesn't matter. Okay, so this is just a figure to show you that our calculated value is more extreme than the value from the table, and so we can reject the null. So we are in the rejection region. Okay, basically that's what it is showing. Okay, now let's talk about a two-tailed test. So what's a two-tailed test? Where we have the null as mu a is equal to mu b, and the alternate is mu a is not equal to mu b. Okay, and it says double the, so compute, and the steps are going to be the same. Compute the test statistic, and then if we are using absolute value approach, then we don't need to worry whether we are in the upper tail side or the lower tail side, as I'll show you. But if you want to follow this approach where you don't use the absolute value, then you just see whether you are in the upper tail or in the lower tail. If you're in the upper tail, then you compute the probability of z being more than equal to the test statistic, and if you are in the lower tail, then you compute the probability of z being less than equal to the test statistic. And the main thing is that to get the p-value, we, as I showed you in the beginning, p-value is going to be twice the probability. Okay, and we reject null if p-value is less than equal to alpha. Okay, so let's jump into a question which will explain things more. A tube of Superwhite toothpaste should have a mean weight of 6 ounces. See, it says the toothpaste should have a mean weight of 6 ounces. So it's not giving us the direction. It's just telling us it should have a mean weight of 6 ounces. So it's a typical quality control problem, because what happens is that the machine can continue to function if the mean filling weight is around 6 ounces. Otherwise, you will have to stop the process and readjust the machines. Okay, so in this case, the null is mu is equal to 6 ounces, and the alternate is mu is not equal to 6 ounces. It's a two-tailed test. Okay, and we will either, so we can reject null if p-value, which is going to be twice the probability, is less than equal to alpha, or absolute value of z calculated is more than equal to absolute value of z alpha by 2. Okay, so here's the question. A sample of 30 toothpaste tubes, so 30 toothpaste was taken, the sample, so n is 30, so A sample of 30 toothpaste tubes has a mean weight of 6.1 ounces. Population standard deviation is 0.2 ounces. Because sigma is given to us, we will use, so this is sigma, we will use Z distribution. Perform a hypothesis test at 0.03 level of significance, so alpha is 0.03, to check if sample weight is 6 ounces. So remember, the null was mu equals 6, alternate is mu not equal to 6. Let's calculate the z-score is x bar minus mu over sigma divided by square root of n. X bar is 6.1. Remember, 6.1 ounces based on 30 toothpaste tubes. Mu is 6. Sigma is 0.2 and n is 40 toothpaste. So this is equal to 6.1 minus 6 divided by 0.2 divided by square root of 40, which comes to 2.74. Okay, so if z is 2.74, then this area is 0.9969, right? And then this area is 1 minus 0.9969, which is equal to 0.0031. Okay, now p-value is double this probability, so twice the probability, which means twice of 0.0031 equals 0.0062. Okay, now how much is our alpha? Alpha is 0.03. Okay, so our p-value, as we can see, is less than equal to value alpha 0.03. So our p-value is less than equal to alpha, so that means we can reject null, which means if we reject null, it means that yes, it looks like from our data that the filling process should be corrected because the mean weight of 6 ounces is not being maintained, right? So these are the steps that we just did. We formulated the null and the alternate. Alpha is 0.03, z calculated is 2.74, and our p-value is 0.0062. Because p-value is less than equal to alpha, we reject the null. Okay, now remember, in a two-tailed test, we don't know whether we are on the lower side or we are on the upper side, and that's why we are multiplying the probability with 2, because we don't know whether we are here or here. And if you remember from chapter 4, when we have two events and we are trying to find the probability of A or B, we just add the probabilities. So in this case, we are going to add the probability of the left region and the right region, and therefore the p-value is 0.0062. Okay, now let's go to the do the same question using the critical value approach. Okay, so remember, critical values will occur in both the lower and the upper tail. So you find the z alpha by 2 value and reject null if z is less than equal to minus z alpha by 2 or z is more than equal to z alpha by 2. This is one way of doing it, or the other way is just find the absolute value of z calculated and compare that with absolute value of z alpha by 2 and reject null if this is true. Okay, so let's go back to our question and do it. A sample of 30. Oh, did I make a mistake? Did I say it's 40 here? Oh yeah, I'm sorry. So can you just make a correction here? I'm sorry about this. It says a sample of 30 toothpaste tubes, and I think I made an error here. So it's n is not equal to 40, n should be equal to 30, and so this should be 0.2 divided by square root of 30. But I guess you will get the value of 2.74, right? So apologize for that. Yeah, so n is 30 because the sample size is 30. Okay, so let's go down to now critical value approach question. So just going up. Yeah, right here. Okay, so sample of 30, so n is 30. So remember, we've already formulated the null and the alternate. The null is mu equals to 6, alternate is mu is not equal to 6, and z calculated was already 2.74. Okay, alpha is 0.03. Now remember, it's a two-tailed test. So we need to find alpha by 2, which is going to be 0.03 divided by 2 is 0.015. Okay, so if this area is 0.015, right, and if we look up the z table, you will find that the z score comes to 2.17. Okay, so our rule here is reject null if absolute value of z calculated is more than equal to absolute value of z alpha by 2. So this, as I told you, is the test statistic, and this is the critical value from the table. Okay, so our calculated value was 2.74, and the absolute value of 2.74 is 2.74, and the value from the table was 2.17. Absolute value of 2.17 is 2.17. So yeah, our calculated value is more than the value from the table. So the same result as before, reject null. Okay. Okay. Now let's look at the critical value the confidence interval approach that we learned in chapter 8, in which what we do is we use sample mean x bar to estimate confidence interval for population mean. Remember, in chapter 8 we did find the confidence interval, so mu was equal to x bar plus minus z alpha by 2 times sigma divided by square root of n. So we find the population mean confidence interval for population mean using this formula, and if this confidence interval includes the hypothesized value mu naught, we do not reject the null, otherwise we reject the null. Okay, and we reject the null even if mu naught is equal to one of the endpoints of the confidence interval. Okay, so in the previous example, if you find remember in this example, we were told that alpha is 0.03. So confidence level 1 minus alpha is 0.97. And then alpha by 2 is 0.015. And z alpha by 2 is going to be 2.17, that we already know. So if we calculate mu is equal to x bar plus minus z alpha by 2 times sigma divided by square root of n. So x bar is 6.1 plus minus 2.17 times 0.2 divided by square root of 30. This comes to 6.1 plus minus 0.07924, right, as is given here. And it ranges from 6.02 to 6.1. Because the hypothesized value mu naught is 6 and it does not lie in this interval, we conclude that the null hypothesis can be rejected. Okay. Okay. Now let us look at what happens if sigma is unknown, right? So if sigma is unknown, as we learned in chapter 8, then if sigma is unknown, we use the T formula, which is equal to x bar minus mu or mu naught divided by sample standard deviation divided by square root of n. And we use T with n minus 1 degrees of freedom. The other steps remain the same as before. So let's jump into a question. Yeah, and the rules will remain the same, so I'm not going over the rules. I've already explained them in the beginning, and I'll explain them to you again through an example. Okay, so let's go to an example. Let's say traffic police is testing car speeds and the null is mu is less than equal to 65 kilometers per hour. Okay, if null is rejected, police will install radar trap. So basically what is happening is that say the police is testing whether cars are speeding up. If they do, then they're going to install a radar trap. So the null is mu is less than equal to 65. So the alternate is mu is more than 65 kilometer per hour, and this is a one-tail test, right? A one-tail test. A sample of 64 vehicles shows mean speed of 66.2 with a standard deviation of 4.2 km per hour. Use alpha 0.05 to test the hypothesis. Okay, so because we are given sample standard deviation, remember a sample of 64 vehicles shows mean speed with a standard deviation. So S is 4.2 km per hour, and we will use T distribution. X bar is 66.2, alpha is 0.05. Okay, let's calculate T. So T is X bar minus mu divided by S divided by square root of n. X bar is 66.2 minus mu is 65 divided by sample standard deviation. S is 4.2 divided by sample size is 64, so square root of 64, and this comes to 2.286. Okay, so it comes to 2.286. Now we need to use the T table, but let me just okay. I'm just opening my T table on the other side. Okay, so remember we have to use n minus 1 degrees of freedom to calculate the T value, to calculate the probability. So if this is 2.286, and if we are looking at the probability for 63 degrees of freedom, because n minus 1 degrees of freedom means we have 64 minus 1 equals 63 degrees of freedom. So if we look at 63 degrees of freedom and 2.286, so 2.286, you will find that 2.286 is, so 2.286 is between t-scores of 1.998 and 2.387. Okay, which means that p-value is between 0.025 and 0.01. Okay, because our test statistic is 2.286, and this is between 1.998 and 2.387 on the T table, and therefore the probability which is the p-value, because of one-tail test, remember in a one-tail test p-value is equal to 1 times the probability, so p-value is between 0.025 and 0.01 if you look at the top of the table. Okay, so we don't need to find the exact p-value, and I'll tell you why. Because okay, so we just calculated that test statistic was 2.286. So as I was telling you, p-value, it's a one-tailed test, p-value is 1 times the probability, and it is between 0.025 and 0.01. Now in this question, the alpha level that is given to us is 0.05, right? Alpha that is given to us is 0.05. So no matter which value you take, whether you take 0.025 or 0.01 or any value in between, the entire interval is going to be less than equal to 0.05, right? This entire interval is less than 0.05. So that means any p-value in this region, in this interval, is going to be below alpha, and therefore we can reject null. We don't need to find the exact p-value. We can just reject null on the basis of this interval, right? Yeah. So for t equal to 2.286, the p-value is less than 0.025 and greater than 0.1, right? So 0.01 is less than p-value is less than 0.025, and because this entire region is less than 0.05, we reject the null. Okay, and we think that on the basis of this test, that cars are speeding up and that police should install a radar trap. Okay, now if you were to use a critical value approach, okay, if you were to use a critical value approach, remember alpha is 0.05, so, and it's a one-tailed test. If alpha is 0.05 and for n 63 degrees of freedom, our t-score from the table for 63 degrees of freedom will be 1.669, right? So absolute value of t calculated versus absolute value of t alpha from table. So our calculated value was 2.286, and compare that with 1.669 absolute value. So 2.286 is more than equal to 1.669, and therefore we can reject null. Okay, the same result as before. Now you will notice that I keep saying to the calculated value more than equal to value from the table. The reason being that even if the two are same, even if the two are equal, we can still reject the null. So the calculated value doesn't always have to be more than the value from the table. Even if they're equal, we will reject the null. Okay, so that is this is what we just did. So our calculated value is actually falling in the rejection region, the red region, and therefore we can reject the null. Okay, so this brings us to the last concept here, which is called the errors in hypothesis testing. So before coming to this table, let me explain through an example. And this is probably the example is a little bit too contextual right now, and I don't want to get too much into detail in terms of the context here because don't want to cause any anxiety. But let's say that a company is developing a new medicine, right? And they're null, and they're basically obviously they want the new medicine to be better than the old medicine, right? So the null hypothesis is that the alternate hypothesis is that the new medicine is better than the old medicine, and the null, of course, is that the new is not better than the old medicine. So it's either the same or less than the old medicine, right? Because the alternate is that the new medicine is better than the old medicine. Now, the way you test the medicine is that you test the medicine on a few people, and once you have tested the medicine on a few people on your sample, you conclude that the new medicine is better, so you reject the null and you say, oh yeah, the new medicine is better than the old medicine, and you introduce it into the market. Now, once a lot of people take it, people find out later that the medicine had no effect. It was not better than the old medicine, right? So the hypothesis testing that you did on the basis of your sample was incorrect, and that is called a type 1 error. So how do we look at a type 1 error? Well, remember there's a sample condition and there's a population condition. Population condition is when you can test on every single person in the world, okay? And sample condition is the one where you can only come up with your result on the basis of your sample, which is the general case, right? You can't test the medicine on everybody in the world. So in this case, what you said was based on your sample, you said, let's reject the null. On the other hand, if you tested the medicine on everybody in the world, then the null was true. In other words, you would not reject the null, but on the basis of your sample, you rejected the null. And so you made an error, and this is called a type 1 error. Okay. And the probability of making type 1 error is alpha. Remember alpha, our level of significance. So alpha is level of significance, or the risk level, which we have generally been taking as 10%, 5%, or 1%, right? So 0.1, 0.05, or 0.01. So that is alpha, right? So then the question is, well, if the probability of making type 1 error is alpha, then why don't we reduce alpha to as low as possible and reduce the probability of making type 1 error? Well, if we keep on reducing the probability of making type 1 error and for the same sample size, then we run into another problem which is called a type 2 error. So for that, let's go down to another example. Okay, so let's say this company that had developed the medicine and found their sampling, their hypothesis testing to be incorrect, and introduced the drug in the market was penalized heavily by the government. Now, some years later, they come up with another medicine, and again their alternate hypothesis is that the new medicine is better than the old medicine, and the null of course is that the new medicine is not better than the old medicine. It's either the same or worse than the old medicine, right? So they test the medicine on a few people, right, as is possible. They do a sampling and conclude that the new medicine is not better. So they cannot reject the null. They cannot reject the null, and they say, oh, the new medicine is not better than the old medicine, right? So they don't reject the null. However, in reality, if they had introduced the medicine in the market and the medicine had been taken by everybody in the world, or by the population, or more and more people, as more and more people took the medicine, they would have found that the medicine did work. Okay, and since the medicine was never introduced into the market, so it's like a lost opportunity for both the society and the company, and so that is called a type 2 error. Okay, so what is a type 2 error? Now, based on your sample condition, you're saying you do not reject the null. But if you tested the medicine on everybody, so the population condition is that the null is rejected and the alternate is true. Okay, you would have rejected the null and you would have said the alternate is true, but on the basis of your sample, you're saying do not reject the null, right? So that is called a type 2 error. Okay, so um, type 1 error is when you say you reject the null, but actually you should not have rejected the null. And type 2 error is when you don't reject the null, but actually you should have rejected the null, right? So you see how there's always a trade-off between the two. So what should we do? Well, the best way to eliminate errors is to do a census, but it's not possible. It's not always possible, especially when you're testing new medicines. So then what we do is we can reduce the level probability of making type 1 error, and wherever possible, we try to increase our sample size, right? So that's why it is said that take as large a sample as possible when you're doing hypothesis testing. Okay, so I hope that is clear. And with that, we come to the end of chapter 9 notes, and then in my next video I'm going to go through some of the questions that I've suggested that we do from this chapter. So I'll go through some example questions and I'll explain them to you. Okay.